Hey, nowadays we often take it very much for granted that we can go to an airport, get on a plane and arrive safely at our destination. However, behind the scenes there are a lot of critical factors that ensure this can happen safely for the passenger, but also profitably for the companies involved. For example, it can cost an airline up to $200,000 a day for a plane to be sat on the tarmac waiting for maintenance. This makes on-time aircraft movement a critical success factor. So Johannes, perhaps we can start with just a real basic overview of the aircraft market. What is it that sets this industry apart from many others?
So aerospace is pretty unique due to, I would say, a series of factors. I mean, first, safety is paramount to a degree that if you fail, you literally kill people pretty much swiftly. There are other industries where security is paramount. But yeah, I would say aerospace has to deal with an amount of technology, of diversity of technologies that is absolutely huge. I mean, yes, a chemical factory is very dangerous, and you need to pay a lot of attention to security. But in an aircraft, you have everything. You need to have like electronics, parts that are under high pressure, high temperature, parts that operates under vacuum. You need to have parts that are super light, super robust, that can resist against very diverse weather conditions, extra. And all in all, you also have to be very, very cheap, because nowadays you can travel very far for amounts of money that are actually extremely low and that are only a small multiple of the cost the company has to invest in actually in jet fuel.
Okay, so let's talk about sort of the maintenance. How does it actually kind of work in practice?
So the thing to consider is that an aircraft is going to live for, let's say, 3-4 decades. So it is very, very actively maintained. So it's not like you buy an aircraft and this thing just fly until it's retired. It's pretty much everything in an aircraft is going to be inspected, potentially repaired, and so maintenance is literally what keeps aircraft flying. So that means that the whole aerospace supply chains are completely geared toward keeping the aircrafts flying safely by maintaining them according to very, very high standards of, I would say, of security.
So if we take sort of a Lego brick example, when we talk about an aircraft, it's basically made up of many blocks, and all those blocks are sort of interchanged. So how many sort of components are we talking about here? What's the scale of operations?
A commercial aircraft is something like 200,000 or 300,000 different parts. 200,000 or 300,000 different parts. So it's an astonishingly large number of parts. Many of those parts will be changed very, very infrequently, or may not even be changed once during the whole life of the aircraft. But some of them are changed actually very frequently, like let's say tires, for example, that needs to be changed after a certain number of flight cycles. So you take off, you land, and after a certain number of those cycles, you need to change the tires.
Okay, so with so many hundreds of thousands of parts, it's going to have a really sort of complex kind of supply chain attached to it. So what are the complexities that we really associate with this supply chain?
In aerospace, unlike, I would say, most supply chains are just are forward supply chains. So basically you go from producer of raw materials, and then you transform, you combine, you assemble, and then you distribute to your end consumer. You know, the supply chain has a direction. It goes forward from basically producer to consumers. In aerospace, it's completely different. It's mostly about the fact that whenever you mount something on an aircraft, you unmount something. And so why do you do what it's typically called a component change? So why do you need to do that? Well, as I said, aircraft are very, very long-lived, but all their parts are inspected on a very regular basis. So you spend your time unmounting parts, repairing them, which typically is about first inspecting that the part is completely flight capable. But so you spend your time on actually dismounting components and remounting components, and having all those components repaired. And those components, once they are ready to fly, they are deemed as serviceable. They can be serviced on an aircraft. And so your supply chain is basically a whole set of loops where you have components that are taken off aircrafts. They are now unserviceable. They are going to be moved toward repair shops until those components are repaired, and then the parts are deemed, or the components are deemed serviceable, and they are mounted back to aircraft. So your supply chain is absolutely not something that is like forward, producer to consumer. It is, those parts are produced by OEMs originally, but then the cycle between aircraft and repair shops for their entire life.
Okay, I'm not the most nervous of flyers. However, this idea of having a large proportion of parts being repairable is it's a bit of a funny idea. So how many as a percentage, how many parts on a plane are actually repairable and how many are just fully replaced by new parts?
Well, I don't know exactly the percentage, but in terms of value, probably something like 90% of the value of the aircraft is made of expensive components called rotables that can be repaired. So it's so the vast majority of the components can be repaired because the safety standards are so high in aerospace. A repair doesn't mean that the part is broken. It's more like you have a component maintenance manual that basically defines a maintenance schedule. So typically when you say that a part has to be repaired, it's not that it was broken. It's according to its maintenance manual, the parts has to be taken off the airplane to be inspected and validated that basically the part is still fully flight capable. So usually for many parts, actually nothing really happen, not necessarily during the repair. There might be just an inspection and then the part is deemed, perfectly safe and remounted on the aircraft. Some parts are actually repaired, and they are very specific parts that will typically get gradually degraded as the aircraft fly. That can be, for example, the blades in a jet engines or the tires that are used to land the aircraft.
Okay, so let's talk about the stock that the maintenance companies are having to hold. Basically, the idea behind the plane is it's now going to spend probably more time in the air than it actually does on the tarmac. So does this mean the airline companies are having to hold huge amounts of stock?
So yeah, I mean, the key idea is that when you have nowadays, when you have aircraft, you want to keep them flying all the time because an aircraft is a very, very expensive piece of equipment. And basically, if your aircraft doesn't fly, it's money that you're losing, by the hour, because you could actually use this aircraft to transport passengers. So most of the airlines, and that basically, by the way, that was the whole idea behind the low-cost airline, was to have aircraft that flies literally all the times. And for every single travel that they do, you want to have your aircraft full of passengers all the time. So the whole economics behind low-cost airlines is not that you get, I would say, a cheaper maintenance. The maintenance is exactly the same. It's basically defined by the original equipment manufacturer or the aircraft manufacturer. So you cannot adjust anything, and you just want to have your aircraft that is fully utilized. But then that means that in terms of maintenance, you have a very specific asymmetry, which is if you have only one part that is missing, this part, no matter how cheap, can keep your aircraft on the ground. That's called an AOG incident, aircraft on the ground. It just means that something is missing to properly maintain the aircraft, and so you cannot you cannot fly anymore.
So what are the options that are open to an airline company if they've got this one component that's kind of missing?
I mean, worst case scenario, they need a replacement aircraft. So that's very, very expensive, and it's probably going to get even more expensive in the future, because you see, as all companies are now, I would say, leaner and leaner, it means that no company has pretty much any interest in maintaining spare flight capacity. So your alternative is to figure out to get a spare part. You know, you have a part that is missing, so what do? You want to get a spare, and you need to have a serviceable one. So that's the trick. You need to have a spare part that you're allowed to mount on your aircraft. So it's distinction between, you know, unserviceable and serviceable parts. So and here most airlines and most aerospace companies, they have AOG services. So they are like desk, or you can actually call and have, I would say, an emergency quote to say, I need this part, can you provide it to me? And the answer can be yes, but at a steep price. And then the airline companies will corroborate in a very, very short time frames. I mean, in the order of magnitude of 1 hour or so, just to have the parts being delivered to the airport where it's needed. I mean, typically, if you want to have like a part being delivered in 1 hour, it means that it has to be a part that is coming from another airline from the same airport, you know, otherwise it's going to take more time than that.
So what you're sort of saying is the airlines are actually working together quite a lot.
Yes.
I mean, isn't it in their interest to see another company lose money and another company sort of fail?
Yeah, but I mean, on the long term, yes, but the short term, there are, I mean, the aerospace industry is highly, highly collaborative. That's also something that people may not realize, is that all those companies compete, but they collaborate a lot, because you see, if your flight is cancelled, chances are that you're going to take a flight with another company. All those companies, they collaborate for security, they share the same infrastructure that are the airport. So it's, yes, there is a lot of competition, but there is a lot of cooperation as well.
Okay, let's sort of move on now and sort of talk about the forecasting side of things. From what you've described, we're talking about hundreds of thousands of components, you've got repairable loops, you've got potential collaboration between different companies. It sounds like a complete mess, if we're being honest. So how can we actually even begin to approach forecasting for this sort of scenario?
So that's very, very interesting. I mean, first, you have to understand that you typically want to forecast not only the demand part, but pretty much all the interactions and all the things that happens in your aerospace supply chain loops. Because the idea is that when you buy a piece of equipment, you're going to be stuck with it pretty much forever. Remember that this piece of equipment is repairable. So the idea is that if you buy one extra piece of equipment and it's not mounted on an aircraft, it's just going to wait until it's actually being requested. But the thing is that if you have other compatible pieces of equipment, those pieces of equipment may be used as well, and they get repaired. So again, if we compare to a traditional situation, supply chain situation, where you're thinking in terms of replenishment, replenishment, you have clients, they pass orders, they consume the inventory that you have, and when your inventory is a bit too low, you pass a reorder. How does that translate? And this replenishment is basically performed based on a demand forecast. But how does the situation translate in aerospace? An aerospace situation is very different. Why? Because if you have a part that is actually requested from you, it means that this part is going to be, serviced to the end consumer, which is going to be an aircraft at the end of the day, mounted on the aircraft. And if you mount anything on an aircraft, you dismount something, preservation of mass of the aircraft. So if you mount something, you dismount something. So there is a part that is going back to you. And the trick is that if you had like instant repair, then you would only need one spare part of every kind for your entire fleet. Whenever you dismount something, you immediately repairs that part, and this part becomes serviceable again and can be remounted on another aircraft immediately. So you would only need, a tiny amount of inventory of parts, because you would just instantaneously repair the parts, so that whenever there is a demand, you just ship the free part that you have, get back the other one, repair, and be available, to service the part again. But the reality is that those repairs takes time. I mean, there's plenty of things that takes time. So first, the end consumer will have to return the part. That may take indefinite amount of time, so that there is some erraticity. Then it has to be transported to the repair shop, again, varying amount of time. Then the repair shop needs time to do the repair. The amount of time it takes to do the repair depends on the workload that the repair shop has. And the problem is that the workload depends on whatever they are repairing, which are other parts. And then once it's the time also depends on the type of operation that has to be done on the part. So imagine a repair shop just get a big component, but they only have capabilities to do only certain classes of maintenance operations. So they open the component and they decide, oh, this type of repair, we can't do it. We don't have, the accreditation, we don't have the equipment to do this maintenance operation. So sometimes a repair shop will get a component, open it, and decide that they cannot do the repair, and they have to forward the component to another more specialized repair shop somewhere else to do that, and then get back the component. And so it's not just, back to the forecasting question, sorry, it's a long-winded answer. It's not just forecasting the demand, it's forecasting all those delays and ultimately how many extra parts that you have that are not readily attached to any aircraft that you're actually serving.
So the thing I can really understand how you can forecast the demand. I can understand how a certain set of plane tires will do a certain amount of takeoffs and landings before they need to be replaced. But we've got so much erraticity with this kind of repairable process. How can you possibly approach that? How can you possibly know if something's going to be repaired in 2 weeks or 2 months?
So, I mean, the short answer is you don't know. And that's the big, I would say, trick behind probabilistic forecasts, is that there is, I would say, an irreducible uncertainty about when you will need a specific part, especially when you have, let's say, you're a sizable company, let's say a fleet of 100 aircraft, you have some parts that you will only need like 3 times a year for your entire fleet. So it's very rare, it's going to be very erratic. And I mean, although there are some people who are doing some progress with predictive maintenance, which is like having sensors on the components themselves to predict when they will have to be maintained, etc., etc. Overall, it still remains a very, very erratic process. But the good news is that there is some structure to this erraticity. It's not completely random. I mean, you have parts that you need to maintain like every month or so, some parts that you need to maintain once a decade. So it's not completely random. And you have this one big asymmetry, which is no matter which part is missing, in the end, it will keep the aircraft on the ground. I mean, if it's a part that is called a no-go, so basically if you don't have this part, your aircraft is on the ground. For any no-go part, this part has the potential to keep your aircraft on the ground. So it's not just the average demand that is of interest. What you truly want to optimize is the best supply chain decision, which is to have an extra part in stock or not, considering the cost of the part and the cost of not having the part.
Yeah, and like this cost is a very interesting sort of concept, because these airline companies are multi-million-pound companies. They've got a lot of money behind them, and the cost of having an airplane just sort of sat there on the tarmac is incredibly large. So why can't they just have lots of parts in stock and take that sort of cost within?
I mean, they already do. And that's, I mean, for our largest clients, we are talking of stocks that are valued, above 1 billion euro or dollars. So the idea of just having enormous amount of stocks, it's basically been there, done that. So, but there are limits, because you see, if you have literally mountains of stocks, I mean, those parts are very long-lived, true. So it's an asset that you can value in your company books. But ultimately, if you have a mountain of parts attached to an aircraft or a type of aircraft that stop flying, or your end clients don't have those type of aircraft anymore, then basically you end up with a massive inventory write-off. So you can't just say, I'm going to have like mountains of inventory and they will preserve their value forever. It's not entirely true. I mean, the aircraft are very long-lived, but in a given market, customers expect, to have certain type of aircraft that are, that are less noisy, that pollute less and whatnot. And so you cannot assume that the parts that you've acquired will preserve their value forever. And again, airline companies now are trying to be leaner than ever.
Okay. I think it'd be really interesting for our viewers to sort of hear about some of your experiences. So what are the real sort of challenges you've kind of faced when it's come to forecasting for aerospace clients?
So one of the, I would say, one of the challenge that is very surprising is just counting the parts. It might be surprising because, again, in aerospace, you have complete traceability. So for any, rotatable part, you typically have access to the entire history of the parts. Where it was maintained, the aircraft, where it was attached during its life, the number of, I would say, flight hours and flight cycles it has lived through, the whole maintenance program for this component. So you know everything. So why is just counting parts so difficult? The answer is that in aerospace, everything is kind of moving all the time. So you want to know how many parts do you have that are, one of the KPIs you want to count is for every type of part, you want to know how many parts you have that are not directly attached to your fleet. That's the kind of free parts, free to be not attached to an aircraft, and that can be repaired, and that can basically build up your stock of serviceable parts. But you would say, okay, I can just count them, but it's very, very tricky. Why? Because you have parts that are all over the place all the time. So you have parts that are being shipped, on their way to an aircraft. You have parts that are on their way back from an aircraft after being dismounted, unserviceable. You also have parts that are back from an aircraft but are still serviceable. Why? Because when you start a big maintenance operation on an aircraft, you don't want to end up the maintenance operation that is like something that is, a very time constraint. You have to do your maintenance under X hour. So typically the crews that operate this sort of maintenance operation, they will ask for more parts than what they really need, because there is some degree of uncertainty. So if they don't know if they will have to change a part, they will ask for the part anyway, maybe to just ship it back, still serviceable, untouched, because in the end they didn't need it. So you have serviceable parts that are traveling both ways. You have unserviceable parts that are traveling back. You have parts that are, I would say, being repaired with very varying, I would say, degrees of delays and of complications. Plus, remember those AOG desks I was discussing before, where you can serve your competitors by giving them, at a price, access to serviceable parts. Well, it turned out that it really complicates also your calculation, because it means that you're either doing a standard exchange or that you're lending parts to the rest of the ecosystem, and the rest of the ecosystem is doing the same thing to you. So when you say, I have 3 serviceable parts, chances are that you've actually you've landed one of those parts to let's say a competitor. So actually you have 4 because you have one that has been landed, but you've been borrowing one from another competitor. So actually you have -1. Then there is a standard exchange that is going on. By the way, a standard exchange is you need a part. I am going to send you the serviceable part, and you're going to send me the unserviceable part. So in the end, it's a swap. I'm sending you a part, and I'm getting a part from you. And where it gets very complicated is that, remember that those frequently we are talking, it's not a part, it's a component made of many subcomponents. So you can end up with all sorts of complications where you do an exchange and the component that you get back has some of its components that have been exchanged, etc. So in the end, just as part, I would say, of the prime challenge in aerospace is just having a very, very clear picture of what do you have as inventory that is not attached to your aircraft, so that you know what you really need to invest in. It's not exactly what do you have as serviceable parts right now that matter. It's more like what is the overall state of your parts across all your networks, so that you know where you should actually invest.
I'll take your word for it. Who knew that counting could be quite so difficult? You mentioned a really interesting word there, which was KPI. From an optimization perspective, what is it that you're trying to optimize? Are you trying to optimize the dollars in terms of profit for an airline? Are you trying to reduce the amount of time so that there's minimum amounts of delays? What is it you're actually trying to achieve here?
It varies, but one of them, I would say, main KPI for aerospace is how many AOG incident, aircraft on ground incident, can you prevent per dollar invested. So that's the idea, is that you are owning inventory, aircraft parts, in order to properly maintain your fleet, to keep it flying all the time. And the metric that you can use to make sure that everything is flying all the time is just to count how many AOG incidents you get. And so the question of the metric, the performance metric that is of one of the highest interest, is how low can you get in terms of dollar per AOG incident. It's very easy to, if you're ready to spend million per AOG incident, to not millions of dollars per AOG incident, to not have any AOG incident ever. But the question is that, can you shrink that to a number that is much smaller? And that's interesting, because this KPI will also let you drive your investment. So you want to invest on the one unit for the one part that per dollar will give you the highest improvement in terms of AOG incident per year that you will avoid, thanks to this one extra unit in your network.
Okay, so to sort of round things up, what is the key sort of takeaway you want people to take from today's episode?
So the lesson would be, don't even try to apply, I would say, classical supply chain models, so safety stock and whatnot, to aerospace. It will not work. You really need a probabilistic approach, and you really need some things that completely embrace the fact that your supply chain is built of loops and absolutely not like a forward flow from producer to end consumers.
Okay, brilliant. So we're going to have to wrap things up there, but thanks very much for telling us a little bit more about the aerospace industry. It's really interesting. So that's everything for this week. We'll be back again next week with another episode, but until then, thanks for watching.